Okay, so I wanted to do that one more example that didn't get a chance to do in class today, with this sign chart. So let's just look through this, and I mean I think the concept makes sense. I'm hoping from how class went today, but if they already give you, let's say, a function algebraically, and so you're not interpreting it from a graph, I just want to make sure we know how to how to interpret that to see, is it speeding up, slowing down, moving left, moving right. This similar things I would ask, if you had a graph of a position versus time, or a velocity versus time graph. Okay, so it gives us the velocity equation, and it actually gives us the derivative of acceleration. So, on an AP exam, most likely you'd have to actually find that derivative. You have a product rule there, chain rule. So it's no big, I'm okay with doing it now, but just to save time. So it says draw a sign chart to analyze the motion. So for my velocity, my v of t, I'm going to draw from 0 out to 10. And I'm going to take and pay attention to the zeros here. So 2 seems to be a critical value because the velocity when t equals 2 is a 0, and so does 4. And I'm just going to keep track of the sign. Is it positive or is it negative? And you could do test points. You can use multiplicity. You can, think about the graph. I like taking one point and then using multiplicity to see, did the sign switch? So for example, I would pick something in this region over here, like maybe 5. And if you input 5, into the velocity function, you're going to get a positive value. So all the velocities here are positive. And since the multiplicity of 4, the factor where that came from, is odd, remember, where are we looking for multiplicity? You're looking at that exponent. It's 1. That means you have to switch signs. You change from positive to negative in the sign. So I know this side here then is going to be negative. And then 2 has multiplicity, this factor of t minus 2 has multiplicity that's even. So the sign's going to match. It's going to bounce. And right now in honors pre-calc, that's sort of what we're doing, where we're graphing polynomials. And maybe you remember this from last year, where you might approach a 0 and it bounces and it comes down and then it goes right back up. That's what that graph would look like. We're just keeping track of the positives, the negatives. Now, if you're not sure, no worries. You could always just pick an element out of this region, an element out of this region, and test it, but it is definitely negative. Now, I want to line up very carefully my acceleration chart as well. So now my a of t starts at 0 and goes to 10. And I want to keep track of key points here. When is that 0? It's 0 also at 2. But then at 10 thirds. 10 thirds is like 3 1/3, right? So we know it's a little bit before 4, so right there. So there's 10 thirds. And again, let's keep track of the sign of our acceleration. You pick something out of this region, again 4 or 5, that's going to keep everything positive. So I know this is positive acceleration. And then because the multiplicity of each of the factors is odd, we know for a fact it's going to switch signs in our sign chart, and that's positive. Okay, and so then what I kind of like to do is think about the different regions here. So maybe pick this yellow here, I don't know. So 2 seems to be a natural break. Then 10 thirds going up there, and then 4, just kind of seeing and comparing, and there's 10 and there's 0. What's the behavior of each? So now, is the particle speeding up, slowing down, or stopped at t equals 2.5? I probably could have answered this without drawing a sign chart, but I do like seeing the sign chart. So if I look at 2.5, 2.5 for velocity is right there in that negative region, and 2.5 for acceleration is right here also in a negative region. So since both a of 2.5 and v of 2.5 are negative, I know it's speeding up. And again, my justification, I could say both v of 2.5 and a of 2.5 are positive. And therefore, we know we're speeding it up to the right. Okay. How many times does it change directions? So we looked at this at a velocity versus time graph, and that's when the velocity changes signs, right? Switches from positive to negatives. And when you look at a velocity graph, that's where it crosses the x-axis. Here, we literally have to see when does it change signs. So, literally from positive to negative. Remember, there's a 0 at 2 and a 0 at 4. But remember, the 0 at 2, it doesn't change signs. It's moving to the left. It pauses momentarily, but then continues to move left. But then it crosses at 4. So it only changes directions once at time equals 4, right? And, at time equals 2, that's certainly a critical value. That's a significant, suspicious point I want to maybe investigate further. But the sign changes at 4 only. Okay, now slowing down to the right. So immediately I'm thinking of the motion to the right. If I'm moving to the right, that means I need to have positive velocity. Because remember, velocity determines direction. Okay. Now, slowing down, so now I need to make sure that my acceleration has the opposite sign. So if my velocity is positive, then I better make sure my acceleration is negative. If I can find a region that satisfies both of those conditions, then I know it's slowing down to the right. So I'm going to start velocity first, and velocity is positive from 4 on. So then I take a look in the interval of the acceleration. Well, is it ever negative at that region? And it's not, right? It stops being negative at 10/3. So when is this slowing down to the right? It's never. Okay. And I can justify that because at no point in time is the acceleration negative while the velocity is positive. Okay. And so, like I said, I just wanted to cover that example. I know we ran out of time in class today, but I still think based on our conversation and looking at your co-formative work that you have a good base for these position, velocity, and acceleration problems. Okay. So very nice job. Keep working and come and always ask questions.